this session, what we'll be trying to understand is the integrated rate equation. We'll be trying to do for zero order reaction and first order reaction. Not only that, we'll be trying to understand the graphical representation of zero and first order reaction and calculate or derive the expression for the half-life of zero order and first order reaction. So let us go on with the first zero order reaction. Okay, so what basically we are doing when we say integrated rate equation, what basically we are trying to calculate is the expression or derive the expression of the rate constant of this particular reaction. Okay, and understand that how does the rate varies with the concentration also. Okay, so we'll try to see that. So for a zero order reaction, okay, let us consider a reaction. Let us say R2 product. Okay, so then the rate law for this reaction will be, so if I take a reaction R2 product, just one reactant, that is R, okay, it is going into some products. Okay, we are not interested in products since the rate will be decided by the reactant, not the product. Then let us take the rate law. So how I can write the rate law for this reaction? So the rate law can be written as rate is directly proportional to concentration of reactant raised to the power 0, since it is a zero order reaction. Okay, I hope now we understand that when we say zero order reaction, it is raised to the power 0. Okay, so if it is the case, then if we introduce the rate constant, then rate will be equal to, now we know that how to write the rate expression. The rate is nothing but minus. I hope we understand. When we write minus, what we mean is that the rate or the concentration of reactant will always decrease with time. So minus d concentration of R, change in the concentration of R with respect to time dt. That is rate. That is the expression of rate. Is equal to, if I remove the proportionality sign, will be equal to rate constant, rate or the concentration of R to the power 0. Okay, will be equal to K, and R to the power 0 will be 1. So what I can write is rate will be equal to minus dr by dt equal to K. Okay, since R to the power 0 is 1. So now what we'll do is, now we'll just rearrange it. So dr dt, I'll bring it to the right hand side. So it will be minus K dt. Once that is done, now since the variables are separated, you can see, okay, one variable that is the concentration of the reactant, another variable that is the time, we have separated it. Now we can easily integrate it. Integrating both sides, what do we get is R will be equal to minus KT plus I. I hope you understand. Integration of dr is R. Okay, integration of dx is x, right? So integration of dr will be R. Constant comes out of integration. Integration of dt will be t plus I, since it is an indefinite integral, as a result of which we introduce a constant which we call as constant of integration. Okay, so where I is the constant of integration. So let us make this as equation 1. Okay, once we are done with that, then we must know what is the value of I. To know the value of I, what do we do is we put some value of T and R. So what do we do is we go for the initial condition. So what do we do is when T is equal to 0. So when the reaction was not started, okay, when the time was 0, okay, when the reaction hasn't started yet. So what is R? R is equal to R naught. Now what is this R naught? When time is equal to 0, nothing has reacted. So whatever is the concentration of R is concentration at time t. So whatever is the concentration of R will be equal to the initial concentration. So R naught is the initial concentration of the reactant. Okay, so I hope everyone is understanding this. At time equal to 0, when time will become 0, then the concentration of the R will be equal to the initial concentration, because the reaction hasn't started. So whatever was the concentration initially, that will be the concentration of R now. So R naught is the initial concentration. So if I substitute this in equation 1, substituting these values in equation 1. Okay, if I substitute in equation 1, what do I get? R naught will be equal to minus K, and time is 0, K into 0 plus I, and R is R naught. Okay, will be equal to, now obviously K into 0 will be 0, so plus I, so R naught will be equal to I. So that means R naught is nothing but, or I is nothing but equal to the initial concentration. So this value of I now will substitute in equation 1. So substituting this value of I in equation 1, we get R will be equal to minus KT plus R naught. Okay, so we will be getting R naught here in place of I. Once we are done with that, then if I just rearrange this, what is the expression of K I will be getting? K will be equal to R naught, okay, minus K, I'll take it to the other side. Okay, minus KT will become plus KT. This R from the left hand side, when it comes to the right hand side, it will become minus R. So R naught minus R, and if T, if I'll bring it to the right hand side, it will be by T. So this is the integrated rate equation of the zero order reaction, or the expression of K for zero order reaction, expression of the rate constant of zero order reaction. Okay, so that is how we derive the expression of the rate constant of zero order reaction, or what do we call it as integrated rate equation for zero order reaction. Now, let us go further more into this zero order reaction. Now, what we'll be trying to do is we'll try to represent zero order reaction graphically. So how we can do that? Graphical representation of zero order reaction. Okay, so we will take equation 2. So what was equation 2? Equation 2 was this: R will be equal to minus KT plus R naught. Now, if I take this equation, okay, which we rearranged and got the final expression. So if I take this expression and compare this expression with the expression of the straight line y is equal to mx plus c. If I compare this y is equal to mx plus c, what will be y? Y will be equal to R. I hope everyone knows that this is the expression of straight line. So y will be equal to R. So y is nothing but the concentration of R. Your m, the slope, is nothing but minus K. X is nothing but T, and C, that is the intercept, is nothing but R naught. So if I'll plot a graph, so I'll plot a graph X versus Y. So I'll plot a graph of actually R versus T. Okay, that is X, or Y is R, and versus T, that is against X. Y plotting against X, R plotting versus T. And that is what we are trying to learn, that how the concentration will change with time. So if I do that, I'll get this plot: time in x-axis, concentration in the y-axis, and see the graph. Okay, the graph is sloping downwards. Now, why it is sloping downwards? Remember that the inclination of the straight line will be decided by the slope of the graph. And over here, the slope is negative. Whenever the slope of the graph is negative, the straight line will be inclined downwards. Whenever the slope is positive, the straight line will be inclined upwards. Here, the slope is inclined, or the slope is negative, so the graph will be inclined downward. Okay, and you can see you have this intercept C, right? C is the intercept. What is that intercept? Intercept is nothing but the intersection point of the line with the y-axis. So at which point the y, or the line, will intersect with the y-axis. So at which point it is intersecting? It will intersect at a point R naught. So just see the concentration which we are taking. So what was our initial concentration? R naught. So this point is R naught. It was the maximum value of reactant, maximum concentration of reactant. Once we took this maximum concentration, as we started the reaction, as the time goes, what happens? The concentration of reactant always decreases with time. We know that because it reacts, right? It decomposes. So you can clearly see that with time, as the time is increasing, what is happening to the concentration of reactant? It is decreasing. So what it tells you, that this is what is actually is the proof, okay, for a zero order reaction with the increase in time, that the concentration of reactant will always decrease and decrease and decrease. So that is what we have been actually doing. in chemical kinetics and learning in chemical kinetics that with time that the rate of reaction, or when we talk about the concentration of the reactant will always decrease, and this graph proves it. Okay, and the slope of this graph, how much it will be inclined, will be decided by the rate constant minus k. Okay, so that is how we understand the graphical representation of a zero order reaction. Now coming for one more topic in zero order reaction, which we called as half-life of a zero order reaction. Now, what do we understand when we say half-life? Remember that half-life is the time. Okay, so over here we are trying to find a time. What time? The time at which half of the initial concentration actually will be reached. Okay, that means at what time the half of the initial concentration will be decomposed. Means, let's say if you start at a concentration of, let's say 100 moles per liter. Okay, I'm taking a random value, let's say 100. At which point of time it becomes 50? Let's say after 5 minutes, you found out that from 100 it became 50. So that much time, that 5 minutes is nothing but half-life for that reaction. So at what time, okay, how much time does a reaction take to reach half of its initial value is nothing but half-life of that reaction. Okay, so if you take 1000, at what time it becomes 500? If you take 1, at what time it becomes 5? Or how much time does it take to become half of it? Sorry, if you take 1. If you take 10, at what or how much time does it take to become 5? So whatever value you start with doesn't matter, but at how much time does it take for the reaction to reach half of its initial value is nothing but half-life. Okay, over here we want to find for a zero order reaction. So the expression for a zero order rate constant or the integrated rate equation, just now what we have done is this, right? K is equal to R naught minus R by T. So that is our rate equation, okay, or the rate constant expression. So once we get that, now we'll put the condition for half-life. Substituting T as T half. So half-life is, we write it as T half. So when time will become T half, what will happen to concentration? Whatever is the concentration will be equal to half of its initial concentration. R naught is the initial concentration. And R, remember that, is the concentration at time T. So remember that when time becomes half, according to the definition of half-life, the initial concentration at that particular moment must be half of the initial concentration. R naught by 2 is the half of the initial concentration. So if I just substitute this value over there, what do I get? K will be equal to R naught minus R will be R naught by 2 and T will be equal to T half. If we do that, then rearranging the equation, it can be written as, if I just bring T half to the left hand side and K to the right hand side, and just simplify this, what I'll get is T half will be equal to R naught by twice K. So that is the expression of half-life for a zero order reaction. Okay, so very important for numericals point, a numerical question. Okay, so that is how we calculate at how much time that the concentration of the reaction will become half of its initial concentration for a zero order reaction. Okay, so that is how we can properly understand a zero order reaction, how to find out its rate constant or integrated rate equation, how do we graphically represent it, and how do we find the half-life of a zero order reaction. Now, similarly, let us try to go for a first order reaction. Okay, so we will be trying to do similar reaction, just the similar, actually simplification part will be slightly different. So consider a reaction. Again, we will be considering the same reaction. Okay, it will be easy for us to consider this reaction, R2 product. Then the rate law of this reaction is, so what will be the rate law of this reaction? Rate is directly proportional to R to the power 1. In our previous case, it was R to the power 0. Now it will be R to the power 1, since it is first order. Then again, we'll be trying to do the same thing. Therefore, rate will be equal to minus dr by dt. Again, I am explaining this. We are writing minus because what do we know is rate will always decrease with time, okay, or sorry, the concentration of reactant will always decrease with time. So this negative denotes the decrease in the concentration of the reactant with time. By dt, how much actually concentration is changing per unit time, will be equal to, if I introduce equal to, so I have to put a constant, that is rate constant k, and r, obviously r to the power 1, so r. So if I actually write it, so therefore it will be minus dr by dt will be equal to kr. Okay. Then if I just rearrange it, if I bring the similar variable on the same side, so minus dr, r, I'll bring it to the left hand side denominator, so it will be r, and will be equal to dt, I'll bring it to the numerator of the left hand side, sorry, right hand side, it will be minus k dt. So now I have separated the variable, so I'll just integrate it. So when I integrate both sides, what I'll get is, I hope you can understand, integration of dx by x is log x. Okay, log base ex. So same way, integration of dr by r will be log r, ln r. Ln means log base e, equal to minus k, integration of dt will be t, plus introducing a constant, that is integration constant, where I is the constant of integration. Now again, what we'll do, we'll use the initial conditions, that time t is equal to 0 and r will be equal to r naught. So what I'll get as I. So again, at time t equal to 0, r will be equal to r naught, where r is the initial concentration of the reactant. In the very similar way, what we have done for a zero order reaction. So now if I substitute this value in equation 1, where I'll put ln r naught and minus k into 0, time is 0. So what I'll get as I. So substituting this value in equation 1, what do we get is ln r naught will be equal to minus k into 0 plus I will be equal to I. So I will be equal to ln r naught. So this value now will substitute in the main equation. So substituting this I in equation 1, what do I get? Ln r naught plus minus kt plus I, that I value is ln r naught. Now it's just simplification now. So what I'll do is now ln r naught, ln r, I'll bring it to the right hand side. So it will become ln r minus ln r, and there is a slight mistake over here. It will not be minus kt, it will be just kt. Okay, please change that. Okay, because since it is going to the left hand side, so it will be minus, it will be just kt. Okay, so it will be 2.303 r naught by r. Okay, so which will be equal to, if you just simplify that, and I hope you can understand, it's 2.303. Okay, why I am doing that? Because it is log base e, which I am converting to log base 10. Okay, so when I convert to log base 10, the factor is 2.303. So this is what I'll be getting, and log r naught minus log r will be equal to nothing but log r naught by r. Okay, so that is what I'll be getting, and please correct this. Okay, this will not be minus, this will be plus. There is a slight typing mistake over there. So please, this will not be minus, this will be positive value. Okay, so if I just rearrange it, so k will be equal to 2.303 and t will go over here in the denominator, log of r naught by r. So that is the expression, what do we call as integrated rate equation, or the value of rate constant for a first order reaction. Okay, so now again, in a very similar way, let us try to find out the graphical representation of a first order reaction. So taking equation 2, so what is equation 2 is this. So let me take the log base 10 form, natural logarithm form. So if I convert them into, or convert this into natural logarithm, I'll get this. Okay, log r naught minus kt by 2.303 and log r naught. So if I'll take this and compare it with the straight line equation, this is y equal to mx plus c again. So what will be y? Y will be log r. In our zero order reaction, what we got is r just. In m, what is m? M is the constant, so minus k by 2.303, that is m. X is nothing but equal to t. Okay, so x is time, and log R naught is nothing but C, that is the intercept. The only difference is before we actually plotted the graph by R and actually R and time, we are now plotting log R versus time. Okay, that's all. So if we plot log R versus time against time, what do we get is, and the slope will be obviously KT by 2.303, not KT, sorry, it will be K by 2.303, and intercept will be log R naught. Okay, so what you will be getting is this. Okay, so time, okay, concentration, and we are plotting log of concentration. When we do that, obviously again I'll get sloping downwards because slope is negative. You can clearly see that. So slope is negative, it will again slope downwards. Okay, what is this intercept? Log R naught. Again it shows the very same thing. Again it is telling the very same thing. When you start with the initial concentration R naught, that will be the maximum concentration. As the time will increase, then the rate will, or the concentration of the reactant will go on decreasing. Okay, and please make a slight change over here. Please don't write this as T, because T is nothing but X. So here it will be minus K 2.303, which you can see in the graph also. Okay, the slope will be minus K by 2.303, not minus KT by 2.303. Okay, there is a slight typing mistake over there. So coming for the half-life of a first order reaction, the expression for a zero order rate constant is K will be equal to 2.303 by T log R naught by R. That is our rate actually equation. Okay, or that is our integrated rate equation. Then again, what is half-life? Half-life is the time at which half of the initial concentration has reacted. So R will be equal to half of the initial concentration. Again, we'll just put that value. So what I'll get? R, this will be R naught, and R will be equal to R naught by 2. Okay, T will be T half. Then if I just rearrange it, R naught and R naught goes, T half, if I'll bring it to the left hand side and K to the right hand side, I'll get T half is equal to 2.303. 2 comes into the numerator, it will be log 2. Now log 2 has a particular value 0.301. Okay, and if you multiply with 2.303, what you get is 0.693 by K. Okay, and T half is equal to that. So that is the expression for half-life. Okay, so that is how we need to derive the half-life of a first order reaction. Okay, so if I try to summarize everything together now, so the summary, so the reaction first order, if it is first order, what will be the expression? K will be equal to 2.303 by T log of R naught by R. And what will be the half-life? T half is equal to 0.693 by K. For zero order, K will be equal to R naught minus R by T, and half-life will be T half is equal to R naught by twice K. This will be very, very important. Okay, if you talk about your board examinations, or if you talk about entrance examinations, this expressions will be very, very important. Okay, various numerical problems. Okay, many numerical problems actually have been asked based on this particular expressions. Okay, so this expression you have to learn by heart. Okay, you have to know this expression. Okay, very, very important in chemical kinetics. Okay, very common questions in your NEET examination, JEE examination, as well as in your board examinations. And one thing, please note it, that if you see the half-life of first order and half-life of zero order, the half-life of first order is independent of initial concentration. Can you see? There is no initial concentration. Okay, and if you see the half-life of a zero order reaction, it is dependent on initial concentration, and it is directly proportional to initial concentration. That means what? If your initial concentration is high, half-life will also be actually more. And if your initial concentration is low, half-life will also be less. So your half-life of a zero order reaction for the same reaction, if you take a particular reaction, first you take a little bit higher quantity and start, your half-life will be higher. The same reaction you try to take and you decrease the amount of reactant what you have started with, your half-life will also be less. It will also decrease. But those things will not happen for a first order reaction. A first order reaction half-life, if you take one particular reaction, it will always remain constant no matter how much you start with. Okay, the time at which it reaches half of its initial concentration, no matter whether you have started with any concentration, always remains constant. You can see it, it is independent of initial concentration. Okay, in examination, in your board examinations, okay, if you see, what is asked is sometimes prove that the half-life of a first order reaction is independent of the initial concentration. That is how also the question is asked. Okay, so what you have to prove is you have to just derive this expression. You have to prove that T half is independent of initial concentration. There is no initial concentration in the expression of T half for a first order reaction. Okay, so that is how we understand the integrated rate equation for the first order and zero order, and is very, very important. I repeat, this will be very, very important for your board examination as well as for entrance and JEE, any NEET or JEE examination or any entrance examinations. Okay, from chemical kinetics, this is very, very important. So that is all about integrated rate equation.